Hello, and welcome back to Sleepy Science. Tonight, we are not looking upward at the stars. Tonight, we are going deeper. Much, much deeper. We are going back. Back through every layer of history that has ever existed beneath your feet. Back through stone and silence. Through ancient forests and shallow seas. Through a world that breathed and roared and rustled long before a single human eye ever opened. Tonight, we are going to talk about dinosaurs. And not in the way you might expect. No thunder, no drama, no scenes of great catastrophe and noise. Instead, we are going to walk gently through what science has uncovered about these creatures. The strange and the tender, the enormous and the surprisingly small, the fierce and the quietly beautiful. We are going to let the ancient world come to you slowly, the way a landscape appears through early morning fog. So settle in. Let your shoulders drop. Let your hands rest. Let the sound of this voice be the only thing asking anything of you right now. Everything else can wait. The world outside can turn without you for a while. If these slow explorations are something you enjoy, please consider liking and subscribing, or leaving a quiet thought in the comments below. It helps others find their way here, one sleepy mind at a time. But for now, all you have to do is rest and let the ancient world carry you. Let us begin. Dinosaurs existed for a span of time almost too large to hold in the mind. When we talk about dinosaurs, we often imagine them as a single chapter in Earth's history, a period when enormous creatures ruled the land and then vanished. But the truth is far grander than that, and far more difficult to fully grasp. Dinosaurs were not around for just a few million years. They were the dominant land animals on Earth for approximately 165 million years. To understand what that means, consider this: the entire span of human existence, from our earliest ancestors walking upright on the African plains, to every civilization, every invention, every story ever written or spoken, represents roughly 6 or 7 million years at the very most. And the modern version of our species, Homo sapiens, has been around for only about 300,000 years. Dinosaurs ruled for more than 500 times longer than we have existed. They watched continents drift. They watched oceans form and drain. They watched mountain ranges push upward from the earth and slowly wear back down again. They were not visitors to this planet. They were one of its most enduring residents. This span of time is divided by scientists into 3 great periods: the Triassic, the Jurassic, and the Cretaceous. Each one was its own world. Each one had its own cast of creatures, its own forests and coastlines, its own quality of light. The dinosaurs that roamed the early Triassic world would barely have recognized the dinosaurs that walked the late Cretaceous. The world itself had changed so much around them. And there is something quietly comforting about that, if you let yourself feel it. These creatures endured. Through heat and upheaval, through shifting ground and changing skies, they found a way to persist, to diversify, to fill every corner of the world available to them. Their patience was written in stone, and we are still reading it. Not all dinosaurs were enormous. When most people picture a dinosaur, they imagine something large enough to shake the ground. A long-necked giant peering above the treetops, or a predator with teeth the length of a human hand. And while those creatures absolutely existed, they represent only a small portion of dinosaur diversity. Many dinosaurs were surprisingly modest in size. Some were no bigger than a chicken. Others were roughly the size of a turkey or a large dog. A dinosaur called Microraptor, for example, was covered in feathers and was small enough to fit in a person's arms. It likely glided or even flew between trees. And it weighed only about 1 kilogram. There were dozens of small-bodied dinosaur species living in forested environments, darting between roots and undergrowth, hunting insects and small lizards, nesting in the low branches of ancient trees. This is part of what made dinosaurs so successful. They were not locked into one body plan, one size, one way of living. They explored every ecological niche available to them. The skies above, the forests within, the open plains, the river deltas, the shallow coastal flats. There were plant eaters and meat eaters, runners and swimmers, and possibly gliders. There were dinosaurs built for speed and dinosaurs built like living tanks. Dinosaurs with elaborate crests for communication, and dinosaurs so plain-looking they could have passed for large birds on a slow afternoon. The diversity of dinosaurs rivals the diversity of mammals alive today. They are not one creature magnified. They are an entire kingdom of life, as varied and surprising as any group that has ever walked the earth. The word dinosaur itself means something tender if you say it slowly. The name was coined in the 1840s by a British scientist named Richard Owen. He combined two Greek words. The first was deinos, which means terrible or wondrous, depending on which shade of meaning you reach for. The second was sauros, which simply means lizard. Terrible lizard, or wondrous lizard. Both feel true in their own way. Owen needed a name for a group of ancient reptiles whose fossilized bones were beginning to appear across England and Europe. The bones were clearly not from any living animal. They were too large, too strange in their structure, too different from anything that walked the earth in his time. He understood, correctly, that these bones belonged to a distinct and separate group of creatures that had once dominated the land. He gave them a name that carried weight, that acknowledged their strangeness and their grandeur. And that name has traveled with us ever since. Through every museum, every textbook, every childhood imagination that ever looked at a fossil and felt the ancient world stir. Terrible, wondrous lizard. A name given in a cluttered Victorian study, now spoken by millions of children in hundreds of languages. Fossils are letters written in stone, and they take an extraordinary sequence of events to form. When a dinosaur died, the odds of it becoming a fossil were remarkably low. Most organisms, when they die, are consumed or decompose. Their bones scatter, bleach in the sun, dissolve in rain. They return to the earth without leaving a permanent record. For a fossil to form, the body, or at least a part of it, needed to be buried quickly, usually by sediment in a river delta, a floodplain, a lakebed, or the shallow edge of an ancient sea. Once covered, the slow work of mineralization could begin. Over thousands, then millions of years, water carrying dissolved minerals would seep through the bone, gradually replacing the original material molecule by molecule until the bone itself became stone. What remains is not exactly the original bone. It is a perfect stone replica, holding every groove and ridge, every hollow chamber and textured surface of the original, preserved in mineral quiet. Then the fossil had to survive. Millions of years of pressure, millions of years of shifting rock layers above it, earthquakes, erosion, the movement of continents. And then it had to reach the surface through the slow wearing away of the rock around it, exactly at a time when a human being happened to be walking nearby. The fossils we have found represent an almost impossibly small fraction of all the dinosaurs that ever lived. Each one is a small miracle of survival, a message in stone that waited in darkness for millions of years, patient and still, until someone looked down and found it. Some of the best preserved dinosaur fossils come from places that were once lush and wet and are now dry and swept by wind. The Gobi Desert, stretching across Mongolia and northern China, is one of the richest places on Earth for dinosaur fossils. It seems unlikely. This vast and windswept landscape of sand and scrub, but tens of millions of years ago, this region was a place of river valleys and forests, shallow lakes and seasonal rains. Dinosaurs lived and died here in great numbers. Many were buried by sandstorms, so swift and so deep that they were preserved almost exactly as they fell. Nests full of eggs, parents curled over their clutches, young hatchlings still near their shells. Entire scenes from a world 100 million years old, frozen in place by an ancient desert wind. Paleontologists have found specimens in the Gobi that still show the positions the animals died in. An oviraptor crouched over her nest, arms spread wide in a brooding posture, protecting her eggs until the very last moment. Velociraptor and Protoceratops locked in combat, their bones intertwined as though the struggle never ended, only paused. These moments of stillness, captured in stone, are among the most intimate things science has ever found. Not just bones, but behavior. Not just anatomy, but feeling. A mother sheltering her young. Two creatures caught in the last moment of a life that was entirely real. Dinosaurs were not cold-blooded in the way we once imagined. For most of the 20th century, dinosaurs were thought of as slow, sluggish, cold-blooded animals. More like giant lizards than anything else. This image shaped how they were drawn, how they were described, how they were imagined in film and fiction. But over the past few decades, that picture has changed completely. Evidence from fossilized bones, from growth rings inside them, from isotope analysis, and from the structure of blood vessel channels running through them, suggests that many dinosaurs were warm-blooded, or at least somewhere in a broad middle ground between the slow metabolism of a reptile and the fast, hot engine of a mammal. Many dinosaurs grew fast, astonishingly fast. A large sauropod, one of the long-necked giants, could add several kilograms of body weight per day during its peak growth years. That kind of rapid growth requires a high metabolic rate. It requires warmth from within. And the feathered dinosaurs, the ones most closely related to modern birds, almost certainly maintained their own body temperatures, generating heat through their own metabolism the way birds and mammals do today. This changes everything about how we picture them. They were not slow and sluggish, basking on sunlit rocks, waiting for warmth from outside. Many of them were active, alert, warm to the touch, burning with their own inner fire. When you think of a dinosaur now, do not think of cold stone. Think of something that breathed and warmed and moved through the ancient world with the urgency of a living thing. The Brachiosaurus stretched its neck toward the sky and fed on treetops that nothing else could reach. Of all the creatures that ever walked the earth, the long-necked sauropods were among the most extraordinary. They were the largest land animals in the history of life. Nothing before or since has come close to matching them in sheer bodily scale. Brachiosaurus was one of the most remarkable of them. It lived during the Jurassic period, roughly 150 million years ago, in the warm and humid forests of what is now North America and Africa. It stood perhaps 9 or 10 meters tall at the shoulder, with a neck that added several meters more. It weighed somewhere between 30 and 60 tons, making it heavier than any land animal alive today, heavier than many large trucks loaded to capacity. And yet, for all its immensity, it was a plant eater. It spent its days moving slowly through ancient forests, pulling leaves and fronds from the tops of tall cycads and conifers, breathing slowly through a long neck, its huge heart working steadily to push blood up through all those meters of throat. Paleontologists have long debated how such a heart could function. To push blood to the brain of a Brachiosaurus, the heart would have had to be extraordinarily powerful, perhaps generating a blood pressure several times that of a human. Some researchers have suggested that Brachiosaurus did not hold its neck fully upright most of the time to reduce the cardiovascular challenge. Others believe the heart was simply enormous enough to manage it. What we know for certain is that it worked. For millions of years, these giants moved through their world, feeding and breathing and resting under the Jurassic sun. To stand beside a Brachiosaurus, even in imagination, is to feel something shift inside you, a sense of scale dissolving, a quiet reminder of how many different sizes the world can hold. Sauropod footprints have been found across every continent, pressed into the earth like enormous stone bowls. In many places around the world, ancient shorelines and river deltas have preserved the trackways of long-necked giants. These are not fossils of bones, but fossils of movement itself, impressions left in soft mud that hardened layer by layer into something that would outlast everything around it. In Texas, along the Paluxy River, enormous sauropod tracks run alongside the smaller three-toed prints of a large theropod. The tracks cross and recross, telling a story that can never be fully known. Was the predator following the giant? Were they simply moving through the same landscape at different times, their paths overlapping only in stone? In Bolivia, a cliff face is covered in hundreds of dinosaur tracks, exposed by erosion from what was once a flattened lake bed. Small footprints and large footprints, some running in clear parallel lines as if a herd had passed. In Australia, the Broome region holds one of the largest and most diverse collections of dinosaur tracks in the world. Sauropods, theropods, ornithopods. Dozens of species recorded in the rock of an ancient tidal flat, still visible today at low tide, washed clean by each returning sea. There is something deeply moving about a footprint. A bone tells you shape and size, but a footprint tells you something else entirely. It tells you direction. It tells you pace. It whispers that something was here, moving through the world, carrying its own weight across a particular patch of ground on a particular afternoon hundreds of millions of years ago. These creatures were not abstractions. They were present. They had somewhere to go. Triceratops may have lived in loosely social groups, and its horns were likely used for display as much as for defense. Triceratops is one of the most recognizable shapes in all of paleontology. That wide, bony frill, the three horns projecting forward from the face, the massive, low-slung body built like a living fortress. It has appeared on children's bedroom walls and museum posters for over a century. It lived at the very end of the Cretaceous period, roughly 66 to 68 million years ago, in the forests and floodplains of western North America. It shared that world with Tyrannosaurus Rex, and there is fossil evidence of combat between them, bite marks on Triceratops bones that match the teeth of a large tyrannosaurid. But not all of Triceratops' remarkable head anatomy was about fighting predators. The frill, in particular, was highly vascular, full of blood vessels, which suggests it could change color or flush with heat. This is exactly the kind of structure you would expect to see in an animal that used visual signals to communicate, to attract mates, to assert dominance within a group, or simply to recognize members of its own kind from a distance. Some scientists have proposed that the frill changed appearance with age, so that a young Triceratops would have looked quite different from a mature adult. This would have allowed individuals to assess the age and status of others at a glance. A simple language written in bone and blood and color. Imagine a herd of Triceratops moving through the late Cretaceous forest. The low rumble of their footsteps, the sound of leaves pulled from branches, the slow turn of frilled heads catching the morning light. A world full of gesture and meaning. A world communicating in ways we are only just beginning to read. Tyrannosaurus Rex had one of the most powerful bites of any land animal in Earth's history. Yet it may have had a surprisingly gentle side when it came to its young. The name alone carries weight. Tyrannosaurus Rex, king of the tyrant lizards. It lived at the end of the Cretaceous, walking the floodplains and river basins of what is now western North America, from roughly 68 to 66 million years ago. Its bite force has been estimated at roughly 35,000 to 57,000 newtons. To put that in perspective, a large lion bites with roughly 4,000 newtons of force. A saltwater crocodile, one of the strongest biters alive today, manages about 16,000. Tyrannosaurus was in a different category entirely. It could crush bone, not just bite through meat, but reduce bone to fragments. This allowed it to access the marrow inside the bones of its prey, extracting nutrition that other predators could not reach. And yet, those same jaws that could shatter bone were apparently capable of extraordinary delicacy. Fossilized evidence suggests that Tyrannosaurus likely engaged in some degree of parental care, at least in the early stages of its offspring's lives. Some paleontologists believe the adults may have carried hatchlings gently in their mouths, as some crocodilians do today. A jaw designed for crushing, holding its young with care. There is something in that contrast that is almost impossible to hold. The most fearsome predator of its age, capable of breaking the spine of a hadrosaur. Also, perhaps, gentle, watchful over its young in the first vulnerable days of their lives. Power and tenderness have always coexisted in the living world. It should not surprise us to find them together in the Cretaceous. Tyrannosaurus Rex had tiny arms that were nevertheless powerful, and their purpose is still debated. Few things in natural history have attracted as much gentle amusement as the arms of Tyrannosaurus Rex. They are comically small in proportion to the animal's enormous body. A fully grown Tyrannosaurus, 12 or 13 meters long, wearing those modest forearms like an afterthought. But they were not useless. The muscles attached to those small arms were, by all available evidence, extremely strong. Some estimates suggest each arm could curl roughly 200 kilograms. They were tipped with 2 clawed fingers, and the bone structure suggests a restricted range of motion, meaning the arms could not reach the mouth and were not used for feeding in the conventional sense. So what were they for? One idea is that they helped Tyrannosaurus rise from a resting position on the ground, bracing against the earth while the massive hind legs pushed upward. Another idea involves courtship, the arms used to hold a mate during reproduction. A third suggestion is that they were used in a grappling hold on prey while the jaws delivered the killing bite. None of these ideas has been definitively proved or disproved. The arms of Tyrannosaurus remain one of paleontology's most endearing open questions. There is something oddly reassuring about that. Even the most famous dinosaur, the one studied for over a century, still holds its secrets, still has something it has not yet told us. The ancient world is patient. It gives up its answers slowly, and always on its own terms. Many dinosaurs were covered in feathers, and the discovery of this fact changed how the ancient world looked forever. For most of the history of paleontology, dinosaurs were imagined as scaly creatures, somewhere between a lizard and a crocodile in appearance. This was a reasonable assumption given what the fossils showed, mostly bones, occasionally impressions of skin. Then, beginning in the 1990s, a series of extraordinary fossils began emerging from the Yixian Formation in northeastern China. These fossils preserved not just bones, but soft tissue, impressions, outlines, and, in some cases, the actual carbonized remnants of feathers. The first feathered dinosaurs found in this region had feathers that were simple, almost hair-like filaments. But as more specimens were found, the complexity increased. Some had full flight feathers on both arms and legs. Some were covered in a dense, insulating layer similar to the down of a modern bird. Some showed evidence of color, preserved in microscopic structures called melanosomes that tell us about pigmentation. One small dinosaur, Sinosauropteryx, was found to have had a reddish-brown and white-striped tail. Another, Ankylosaurus, had black and white patterning on its wings, with a reddish crest. These were not dull or featureless animals. They had the visual richness of modern birds, the shimmer and pattern of living things that communicate through color. The world of the dinosaurs was not a gray and scaly one. It was a world of feathers in the wind, of color catching the light, of creatures dressed in the same kind of beauty we still see in the birds that visit our windows. Because those birds, the ones that land on your windowsill on a quiet morning, are dinosaurs, descended in an unbroken line from the feathered theropods of the Cretaceous. The ancient world did not vanish entirely. Part of it is still here, singing in the trees outside your window. Birds are living dinosaurs, and this is one of the most quietly extraordinary facts in all of natural history. The relationship between birds and dinosaurs was long suspected, but only recently confirmed beyond reasonable doubt. Archaeopteryx, a feathered creature found in Germany in the 19th century, had the skeleton of a small theropod dinosaur and the feathers of a bird. For years, it was considered a transitional form, a creature caught between two worlds. But as more evidence accumulated, it became clear that the line between dinosaur and bird was not a sharp edge, but a gradual continuum. The features we associate with birds, hollow bones, wishbones, feathers, warm blood, the way they breathe, all of these appeared gradually in the theropod lineage over tens of millions of years. Modern birds are technically classified as avian dinosaurs. Every chicken, every sparrow, every heron standing at the edge of a pond is a direct descendant of the feathered theropods of the Mesozoic era. The non-avian dinosaurs, the ones we usually picture when we say the word, went extinct. But the birds carried the lineage forward, adapting, diversifying, filling the skies of every continent. Today, there are roughly 10,000 species of birds alive on Earth. That makes birds more species-rich than all mammals combined. In terms of species count, the age of dinosaurs never really ended. It just took flight. The next time you hear birdsong drifting through an open window, early in the morning, when the world is still soft and quiet, you are hearing the Mesozoic era speaking to you. A line of descent stretching back 165 million years, still singing. Dinosaur eggs came in a remarkable variety of shapes and sizes, and nesting behavior was far more sophisticated than once assumed. The discovery of dinosaur nesting sites has given paleontologists a window into the most private and tender aspects of these animals' lives. Eggs, by their very nature, speak to continuity, to the future, to the quiet hope embedded in every living thing that chooses to reproduce. Dinosaur eggs varied widely in size and shape. The eggs of large sauropods were roughly spherical, about the size of a volleyball or slightly larger. The eggs of theropods were more elongated, like the eggs of modern birds. Some eggs were hard-shelled, others leathery, depending on the species and likely the conditions in which they were laid. In Montana, a site called Egg Mountain, discovered in the late 1970s, revealed something remarkable. Nests of a dinosaur called Maiasaura were found together in large numbers, close enough that the adults would have been aware of one another while brooding. The young in the nests were at various stages of development, and some showed worn teeth, suggesting they had been fed by adults rather than leaving the nest immediately after hatching. This was the first strong evidence of active parental care in dinosaurs. Maiasaura, whose name fittingly means good mother lizard, appeared to have raised its young in communal nesting grounds, returning year after year to the same site. A dinosaur bringing food to her young, watching over them through the vulnerable days after hatching. This is not the cold, indifferent reptile of old imaginings. This is something much warmer, something recognizable. In the business of raising young and watching over the helpless, we are not so different from creatures that lived 100 million years ago. The Stegosaurus had plates along its back whose purpose is still not fully settled, and it may have used them to regulate its own temperature. Stegosaurus is one of those animals whose silhouette is immediately recognizable. The broad, low body, the short front legs, the spiked tail, and rising from the back, 2 rows of large, kite-shaped plates arranged in an alternating pattern, reaching up toward the sky like the sails of some ancient, unlikely ship. It lived during the late Jurassic, roughly 150 to 155 million years ago, in the warm, open habitats of what is now North America. The plates have been the subject of debate for as long as they have been known. Early theories suggested they were armor, providing protection to the animal's spine. But the placement, alternating rather than overlapping, and the fact that they were not fused to the skeleton, makes them poor shields. A more compelling idea is thermoregulation. The plates were richly supplied with blood vessels, and their large surface area would have made them effective radiators of heat. On a cool morning, turning the plates toward the sun would warm the blood circulating through them, gently raising the animal's core temperature. On a hot afternoon, a breeze passing over those same plates could help cool the animal down. A living thermostat, powered by the sun and the wind. But there is also evidence from the vascular structure of the plates that they could flush with blood and change their visible appearance, which opens the possibility that the plates also served as signals, flushing red or pink during moments of arousal, advertising health, attracting mates, warning rivals. A creature using its own body as a billboard, painted in heat and blood, readable across a Jurassic plain. It lived well over 150 million years ago, and it was already fluent in the language of color. The ancient oceans were full of enormous marine reptiles that often get mistaken for dinosaurs, but lived entirely different lives in the water. When people imagine the prehistoric seas, they sometimes picture the creatures they know from the land, scaled up and set loose in the water. But the great marine reptiles of the Mesozoic were their own distinct groups, not dinosaurs at all, though they shared the same ancient world. The mosasaurs were among the most formidable. These were large predatory lizards that returned to the sea, their limbs gradually evolving into flippers, their tails lengthening and developing a shark-like lobe for propulsion. Some species reached 12 or 15 meters in length. They were apex predators of the late Cretaceous seas, eating fish, other marine reptiles, and possibly even prey on the surface. The plesiosaurs were older and stranger. They had broad, flat bodies and 4 large flippers, which they used to fly through the water in a motion more like a bird than a fish. Some had enormously long necks that made up more than half their total body length. Others had short necks and enormous heads, with teeth interlocked in a cage that could trap fish with a single snap. The ichthyosaurs looked uncannily like modern dolphins. A streamlined body, a dorsal fin, a tail fluked like a whale's. They were built for speed, and some of the evidence suggests they were warm-blooded. capable of long migrations through cold ocean waters. These were not monsters from a nightmare. They were beautifully adapted to an ocean that no longer exists, moving through warm, shallow seas, diving and surfacing, following the rhythms of a world that has long since rearranged itself. The ocean has always been full of marvels. It was simply wearing a different face 100 million years ago. The skies of the Mesozoic were ruled by pterosaurs, flying reptiles whose wingspan ranged from the size of a sparrow to larger than any flying creature that has ever lived. The pterosaurs are another group often confused with dinosaurs, though they were close relatives, sharing a common ancestor. They were the first vertebrates to achieve powered flight, taking to the air long before birds existed, and filling the skies of the Mesozoic for over 160 million years. Their wings were not like those of birds, made of feathers. They were membranes of skin and muscle, supported by a dramatically elongated fourth finger that extended backward along the wing. It was an entirely different engineering solution to the same problem of flight, arrived at by a completely different evolutionary path. The smallest pterosaurs were genuinely tiny, not much larger than a sparrow, flitting among the branches of Jurassic forests. But the largest was staggering in scale. Quetzalcoatlus northropi, from the late Cretaceous of North America, had a wingspan estimated at 10 to 12 meters. When standing on the ground, it would have been as tall as a modern giraffe. That is not a flying animal as we usually picture one. That is something at the very outer edge of what physics allows. Researchers have spent decades trying to understand how an animal that large could actually get airborne. The leading explanation involves a kind of pole vaulting launch, using the powerful muscles of the forelimbs to push into the air and then unfurling those vast wings before gravity could win. Picture that, if you like, as your eyes grow heavy. A creature the height of a giraffe, folding itself into the sky. Those enormous wings catching the warm Cretaceous air. Rising, climbing, becoming something improbable and utterly real. Dinosaurs likely communicated in ways we cannot fully reconstruct, but the evidence suggests they were far from silent. One of the lingering questions about dinosaurs is what they sounded like. Hollywood has given us the roar, the thunderous bellow that we now associate automatically with large theropods. But whether that is accurate is genuinely uncertain. Soft tissue does not fossilize. We have bones, but we do not have vocal cords. We have skulls, but we cannot measure the resonating chambers of a larynx or a syrinx that no longer exists. What we can do is look at clues. Some hadrosaurs, the duck-billed dinosaurs, had elaborate hollow crests on their heads. Parasaurolophus, one of the most beautiful, had a long, curved crest that swept back from its skull like a horn. The crest was hollow, unconnected to the nasal passages. Computer models suggest that air passing through this structure would have produced a deep, resonant sound, something between a low bass horn and the bellow of a large mammal. Some researchers, looking at the evidence from birds and crocodilians, the two living groups most closely related to dinosaurs, suggest that many non-avian dinosaurs may not have made conventional vocalizations at all. Instead, they might have made sounds by resonating structures in their bodies, more like the boom of a bittern or the rumbling infrasound of an elephant, felt as much as heard. Low sounds that carried through the air and through the ground itself, felt in the chest before they were heard in the ear. The ancient world was not silent. It was full of sound we can barely imagine. Calls crossing distances, resonating through valleys, reaching into forest canopies, announcing presence, claiming territory, calling out across the long and patient distance between one living thing and another. The Ankylosaurus carried a club on its tail that could shatter bone, and its body was armored like a living fortress. Ankylosaurus was built for survival in a world of dangerous predators. It lived at the very end of the Cretaceous, in the same time and place as Tyrannosaurus Rex, and it was armored accordingly. Its back was covered in thick, bony plates called osteoderms, embedded in the skin like cobblestones set in living armor. On its flanks were sharp spikes. Its eyelids were armored. Even the roof of its mouth was reinforced. It was essentially a living tank, slow-moving and heavily protected. But the most remarkable feature was the tail club. At the end of Ankylosaurus's tail, the vertebrae and osteoderms had fused into a dense mass of bone, forming a solid knob that could be swung with considerable force. Studies of the tail structure suggest it was capable of generating forces high enough to fracture the leg bones of a Tyrannosaurus. There is fossil evidence of ankylosaur tail clubs striking predators. A Tyrannosaurus-related dinosaur found with damage consistent with an ankylosaur tail strike. Not every encounter ended in the predator's favor. Ankylosaurus was not fast, and it was not aggressive in any conventional sense. It was a plant eater, moving slowly through the late Cretaceous landscape, grazing on low-growing vegetation. But if threatened, if cornered, if something large and hungry came too close, it could deliver a response that no predator would forget. Quiet strength, patient armor, the willingness to be still until the moment's stillness was no longer enough. There are many ways to survive in a difficult world. The Ankylosaurus chose its own, and it worked for millions of years. Dinosaurs lived on every continent, including Antarctica, which was once a very different kind of place. When we picture dinosaur habitats, we usually imagine warm, lush environments. Tropical forests, open floodplains under a blazing sun. And while those environments were certainly home to many species, dinosaurs were far more adaptable than that picture suggests. Antarctica today is covered in ice and largely inhospitable to complex life. But during the Cretaceous period, it was a very different world. Though it sat at high southern latitudes, the climate was warmer overall, and seasonal forests of conifers and ferns covered much of what is now frozen ground. Several dinosaur species have been found in Antarctica, including a hadrosaur and a small ankylosaur-related species. These animals would have experienced polar seasons, months of continuous daylight in summer and extended darkness in winter. Whether they migrated away from the polar regions during the dark months, or whether they remained, resting through the winter in some slowed physiological state, is not yet known. But their presence there tells us something important. Dinosaurs were not locked into a single environmental niche. They were explorers in the deepest biological sense. They went where the land allowed, and they found ways to make those places home. From the tropics to the poles, from sea level to high altitude, from dense forest to open desert. Dinosaurs inhabited every continent, in every season, across a span of time that makes all of human history feel like a single breath. The largest dinosaurs needed enormous amounts of food every day, and their digestive systems were engineering marvels. A large sauropod, like Brachiosaurus or Argentinosaurus, needed to consume an astonishing amount of plant material each day just to maintain its body. Estimates vary, but some calculations suggest that a very large sauropod may have needed to process several hundred kilograms of vegetation daily. This posed a significant challenge. Their teeth were not designed for chewing. Unlike mammals, which have complex grinding molars designed to break down plant cell walls, sauropod teeth were simple pegs or rakes, designed for stripping leaves from branches rather than processing them. This means the actual work of digestion had to happen elsewhere, in a large and complex fermentation chamber somewhere in the digestive tract. Some researchers believe that sauropods may have swallowed stones, called gastroliths, to help grind the plant material in their stomachs. This is a strategy used by modern birds, particularly those that eat hard seeds. A collection of smooth, polished stones found in association with sauropod remains has lent some support to this idea, though it remains debated. The sheer scale of the feeding requirements of a large sauropod would have shaped the landscape around it. A herd of such animals moving through a forest would have dramatically altered the vegetation, opening clearings, redirecting rivers of sunlight to the forest floor, creating new habitats for other species in their wake. They were not just inhabitants of their environment, they were architects of it, reshaping the world simply by being present in it. Eating, moving, depositing, resting. A living force of ecological change, enormous and patient and utterly unaware of the landscapes they were making. Pachycephalosaurus had a skull dome so thick that it was used for headbutting, in the same way that some modern sheep and goats compete for dominance. Pachycephalosaurus is one of the more visually striking dinosaurs, though it is less famous than many others. It was a two-legged plant eater, roughly 4 to 5 meters long, and it lived at the end of the Cretaceous in North America. What sets it apart is its skull. The dome of bone on the top of its head was up to 25 centimeters thick, a solid mass of bone that would have been extraordinarily resistant to impact. The long-standing interpretation was that Pachycephalosaurus used this dome in direct head-to-head combat, ramming skulls the way bighorn sheep do today, to establish social hierarchy or win mating rights. And while some researchers have challenged whether the geometry of the skull would have allowed direct head-on ramming without damaging the spine, most agree that these thickened skulls were used in some form of physical competition. Perhaps they butted heads at an angle. Perhaps they used the dome to strike the flanks of rivals, the way some deer use their antlers today. Perhaps the dome was also a signal in itself, a visible indicator of age and strength readable at a distance. Competition, display, and the constant negotiation of social order. These are not behaviors unique to the modern world. They were part of dinosaur life as surely as feeding and sleeping. The ancient world was just as full of personality as this one, just as full of individuals asserting themselves, competing for position, seeking out advantage, finding their place in the social order of the herd. The drive to belong, to compete, to be seen, has been part of life on this planet for a very long time. The extinction of the non-avian dinosaurs was caused by a catastrophe of almost incomprehensible scale, and the evidence of that event is still visible in the rock beneath our feet. 66 million years ago, at the boundary between the Cretaceous and Paleogene periods, something happened that changed the history of life on Earth. A large asteroid or comet, approximately 10 to 15 kilometers across, struck the shallow sea near what is now the Yucatan Peninsula in Mexico. The impact released energy on a scale that is difficult to express in ordinary terms. Billions of times more powerful than the largest nuclear weapon ever detonated. The impact vaporized rock and seawater, sending a plume of superheated material into the upper atmosphere. Around the impact site, the destruction was immediate and total, but the effects rippled outward in waves. Enormous tsunamis, earthquakes registering magnitudes far beyond anything recorded in human history. Wildfires ignited by the re-entry of superheated ejecta falling back through the atmosphere across a huge portion of the globe. Then came the darkness. Dust and soot and vaporized sulfur filled the upper atmosphere, blocking sunlight for months, possibly years. Photosynthesis slowed or stopped in large parts of the world. Temperatures plummeted. Food chains collapsed from the bottom up. In this environment, the large, warm-blooded, high-energy requiring non-avian dinosaurs could not survive. The world had changed too suddenly, too completely, for animals that needed so much food each day. Roughly 3/4 of all species on Earth went extinct in the following thousands of years. It was the most catastrophic mass extinction of the past 500 million years. And yet, life persisted. Small mammals burrowed through it. Some birds survived. Crocodilians endured in their river systems. Some fish, some insects, some plants found shelter in the new cold and dark and came through to the other side. Life, once it has a foothold, is remarkably hard to extinguish entirely. It bends, it hides, it waits, and when the light returns, it begins again. Some dinosaurs have only recently been discovered, and new species are still being found every year. Paleontology is a field where the map is perpetually incomplete. Every year, researchers working in the field and in museum collections describe dozens of new species. Some are entirely new creatures, found in places never previously excavated. Others are animals known from a few partial bones, slowly becoming clearer as more specimens come to light. The rate of discovery has actually increased in recent decades, not slowed down. As paleontologists have expanded their fieldwork into previously underexplored regions, China, Argentina, Tanzania, Morocco, Madagascar, new and extraordinary creatures have appeared. Some have completely changed our understanding of how certain dinosaur groups were related. A single new species, found in the right place, can rearrange the entire family tree. Paleontology is full of these moments of elegant disruption, when a new fossil arrives and everything previously understood has to be carefully rethought. And there are almost certainly many more waiting. In the red deserts of Argentina, in the Jurassic beds of Portugal, in the high-altitude Cretaceous exposures of Central Asia, in river cuttings and road excavations and eroding cliff faces around the world. The ancient world has not finished speaking. It is still sending messages, slowly, patiently, the way ancient things always communicate, on their own schedule, in their own time. Some dinosaurs showed signs of disease and injury, and the evidence of healed wounds tells quiet stories of survival. Bones can be read like diaries, not just for the shape of the animal, but for the history of its life. Paleontologists examining dinosaur fossils have found evidence of broken bones that healed, of infections that left marks in the bone structure, of arthritis, of growths, of injuries sustained and recovered from. A Triceratops specimen has been found with a healed bite wound on its hip, the size and shape consistent with a Tyrannosaurus. The animal survived. It carried that healed scar through whatever years remained to it, walking on a hip that had once been crushed and then slowly knit itself back together. An Edmontosaurus, a large hadrosaur, was found with a Tyrannosaurus bite on the base of its tail, clearly healed, clearly old. The animal had been attacked and escaped. It had carried on. There are sauropods with fractured vertebrae that had partially healed, theropods with broken ribs, ankylosaurs with foot deformities from old injuries. These are not just facts about bones. They are stories about individual animals, about specific moments of pain and recovery, about the will to continue that seems to be written into the structure of every living thing. A Triceratops that survived a Tyrannosaurus attack went on living. It continued to eat, to move through the Cretaceous landscape, to feel the sun on its frill and the ground beneath its feet. Its story did not end on the day of the wound. It continued. Survival is one of the oldest stories life knows how to tell, and it was telling it long before we arrived to listen. The relationship between dinosaurs and the plants they ate shaped the evolution of both. In an ancient and ongoing conversation written in leaves and teeth. Evolution does not happen in isolation. Every plant-eating dinosaur was in a constant, invisible conversation with the plants it consumed, and those plants were, in their own slow way, responding. During the early Mesozoic, the dominant plants were gymnosperms, conifers, cycads, ginkgos, tree ferns. These were tough, often fibrous plants, and the plant eaters of the time evolved accordingly. Tall browsers like sauropods reaching up into the canopies, heavily built ornithischians cropping low-growing vegetation. Then, during the Cretaceous, the flowering plants appeared. The angiosperms, soft, fast-growing, nutritious, spreading rapidly across the landscape. This new resource was exploited enthusiastically by the hadrosaurs, the duck-billed dinosaurs, who had dental batteries of hundreds of tightly packed teeth, perfect for processing the tougher flowering plants of the floodplain. As the plants spread, the hadrosaurs diversified. As the hadrosaurs diversified, the selective pressure on the plants shifted. A slow, patient, million-year negotiation. Two kingdoms of life shaping each other through deep time. The flowers we see today, the grasses that cover so much of the earth, evolved in a world where large dinosaurs were grazing and browsing and reshaping the vegetation. The plants we live among carry, in some small molecular way, the memory of the creatures that fed on their ancestors. The ancient world is not as gone as it seems. It persists in small and quiet ways, in the structure of a flower, in the shape of a leaf, in the particular way a blade of grass bends in the wind. The colors of dinosaurs, once thought unknowable, are slowly being revealed through the study of microscopic structures preserved in fossil feathers. For most of the history of paleontology, the colors of dinosaurs existed only in the imagination of artists. Some chose brown and gray, the safe and conservative palette. Others reached for greens and yellows, echoing the colors of modern reptiles. For a long time, there was no scientific way to know. Then came the melanosome. Melanosomes are tiny structures within cells that produce pigment. In modern birds, the shape of the melanosome determines the color it produces. Rod-shaped melanosomes tend to produce black or gray. Round ones tend towards reddish browns. The patterns and densities of different melanosome types create the full range of bird coloration. And melanosomes, because of their microscopic size and their chemical stability, can survive in fossils. They have been found preserved in the feathers and feather impressions of multiple species of feathered dinosaurs. And by reading their shapes and densities, scientists have been able to reconstruct color patterns with reasonable confidence. Ankylosaurus, a small feathered dinosaur from China, had black and white wings in a speckled pattern, with a reddish crest on its head. Sinosauropteryx had a reddish-brown and white-striped tail. Microraptor may have had iridescent, glossy black feathers, like a modern starling. These were not dull creatures shuffling through a grey world. They were vivid, ornamented, wearing the same rich visual language of color that birds still use today for recognition, for attraction, for communication. The ancient world was beautiful. We are only just now beginning to see its colors. The world that dinosaurs inhabited was radically different from the one we know, and imagining it takes you somewhere very far from the present. During the Triassic, when dinosaurs first appeared, the continents were still joined in a single vast landmass called Pangaea. The interior of this supercontinent was arid and hot, swept by seasonal monsoons that brought brief floods to dry plains. The first dinosaurs emerged in this world, small and quick, moving through a landscape dominated by other reptile groups that would later dwindle and disappear. By the Jurassic, Pangaea had begun to break apart. The Atlantic Ocean was opening as a narrow seaway. The climate was warmer and wetter across much of the world. Dense conifer forests covered vast areas. Fern understories spread beneath the trees. Shallow seas flooded large portions of the continents. In this lush world, the great sauropods flourished. Dozens of species, each slightly different in proportion and feeding habit, grazing and browsing through forests that no longer exist, along the shores of seas that have long since closed. The Cretaceous brought still more change. The continents continued to separate, creating island land masses and isolated populations that evolved in different directions. Flowering plants transformed the landscape. Sea levels rose and fell. The climate cycled through warm phases and cooler periods. All of this change, all of this shifting of land and sea and climate, played out over millions of years. And through all of it, the dinosaurs persisted, adapting, diversifying, filling each new world that the planet offered them. They were creatures of a living Earth. an earth that moved and changed beneath their feet. And they moved with it, generation by generation, finding each new version of the world and making it their own. The bones of a dinosaur grew in annual rings, like the rings of a tree, recording each year of its life in layered stone. One of the quieter tools of paleontology is bone histology, the study of the microscopic structure of fossilized bone. When a thin slice of dinosaur bone is prepared and examined under a microscope, it reveals layers of growth, compressed and expanded, dense and porous, corresponding to fast and slow periods of growth through the animal's life. In this way, scientists can read the age of a dinosaur at death with reasonable accuracy. They can see whether it was still growing or had reached its full adult size. They can see how fast it grew in its early years, and how that rate slowed as it aged. Many of the large dinosaurs we know from museums are actually adolescents. Sue, the famous Tyrannosaurus Rex in Chicago, was roughly 28 years old at death, still growing, though close to full size. Older, fully mature Tyrannosaurus specimens would have been even larger. What the bone rings also reveal is that many dinosaurs grew very quickly in their early years, reaching close to full size in their first decade or so. This is much more like the growth pattern of a warm-blooded mammal or bird than the slow, indefinite growth of a reptile. In each ring is a year of life, a year of finding food and avoiding predators, a year of seasons changing, of warm, wet months and cooler, dry ones, a year of growth pressed into the calcium of a bone, preserved in stone, waiting in darkness for 66 million years, until someone held it under a light and read it like a book. Deep beneath the feet of everyday life, the bones of dinosaurs are still being found, turning up in the most unexpected places. Fossil discoveries have been made not only in the great open deserts and badlands of paleontology, but in the middle of cities, in construction sites, in the walls of buildings being demolished, under the floors of houses, in the sides of cliffs being cut for new roads. A significant iguanodon discovery was made in a coal mine in Belgium in the 19th century. Dozens of complete skeletons preserved in a single ancient gully. A complete titanosaur skeleton was found by a farmer in Argentina when his dog began digging beside a stone that turned out to be a vertebra the size of a small car. A new species of theropod was identified from bones that had sat in a museum collection for decades, misidentified, waiting patiently on a shelf until someone looked at them with fresh eyes. This is part of the nature of deep time. The ancient world is not only in the distant places, it is beneath us everywhere. Beneath the streets and gardens and car parks and rivers of the present, waiting in the dark geology beneath every footstep you have ever taken. We walk above it constantly, unknowing and unhurried, while millions of years of life lie quietly below us. The ancient world is closer than we usually think. It is as close as the ground beneath your feet, and it is still waiting to be found. Dinosaurs and the forests they lived in were in a deep and ancient relationship, each shaping the other through millions of years of shared existence. When you think of a Jurassic forest, you might picture something like a tropical rainforest today, but the plants were entirely different. No broad-leafed trees, no flowers, no grasses rolling out across open plains. Instead, imagine towering conifers with straight trunks reaching 40 or 50 meters into a hazy sky. Dense tree ferns spreading their fronds across a humid understory. Cycads with their palm-like crowns standing in patches of filtered light. Ginkgo trees, looking almost exactly as they do in cities today. Ginkgo biloba, the ginkgo tree that lines modern streets and sits in botanical gardens, is genuinely ancient. Its lineage stretches back over 200 million years. Dinosaurs ate from its ancestors, rested in their shade, moved through forests where ginkgo was as common as oak or maple is today. When you walk past a ginkgo tree, you are walking past something that stood in the Jurassic, not a replica, not a descendant that looks completely different. Something essentially the same, changed only in small ways by 200 million years of continued survival. The ginkgo watched the dinosaurs come and go. It watched the meteor winter. It watched the mammals diversify. It watched the first humans. And it is still here, standing calmly on a city street, its fan-shaped leaves turning yellow every autumn, as they have turned yellow every autumn for longer than the mind can hold. Some lives are longer than others. Some roots go deeper than we know. The inner ear of dinosaurs tells us about their hearing and sense of balance, and some could hear sounds we cannot. The inner ear is a delicate and complex structure, and in life it is made of soft tissue and would normally decompose without trace. But the bony labyrinth that surrounds the inner ear, the channels and chambers carved into the skull, can preserve for millions of years. By scanning the skulls of dinosaurs with high-resolution imaging equipment, paleontologists can reconstruct the shape of the inner ear and make inferences about what frequencies the animal could hear. The cochlea, the spiral structure responsible for hearing, varies in shape and size in a way that correlates with the range of frequencies an animal detects. A longer cochlea, broadly speaking, means sensitivity to a wider range of sounds. Some dinosaurs, particularly the large theropods, appear to have had hearing tuned to relatively low frequencies. This would have made them sensitive to the deep rumbles and low calls of other large animals, sounds that carried across distance. The semicircular canals, which govern balance, also survive in some specimens. The arrangement of these canals can tell us whether an animal held its head horizontally or at an angle, and how agile it was likely to have been in three-dimensional space. A small, fast theropod with large, complex, semicircular canals was probably highly agile, capable of quick directional changes and precise movement. A large sauropod with simpler canals moved more slowly, with less rapid adjustment. Even in a completely mineralized and ancient skull, the record of experience is still there. How the world sounded, how the animal moved through it, what it heard on a quiet morning in the Cretaceous. Its great ears tuned to the low register of a world still new and unnamed. The migration patterns of some dinosaurs may have rivaled those of the great animal migrations of the modern world. The wildebeest crossing the Serengeti, the caribou moving across the Arctic tundra, the monarch butterfly traveling from Canada to Mexico. These are among the great journeys of the modern animal world, driven by the ancient logic of seasonal change and available food. There is evidence that some dinosaurs undertook comparable journeys. Isotope analysis of dinosaur teeth, reading the chemical signature of different geological regions in the minerals the animal ate, has suggested that some large dinosaurs moved hundreds or even thousands of kilometers seasonally. Camarasaurus, a large sauropod of the Jurassic period, shows isotope signatures in its teeth suggesting it moved regularly between upland and lowland environments, perhaps following the seasonal availability of food. The evidence is indirect, but it points toward behavior familiar to any naturalist today. Hadrosaur bone beds, sites where the remains of dozens or hundreds of hadrosaurs were deposited together, suggest that these animals moved in large herds. Whether those herds migrated seasonally, following the rains and the new vegetation the way wildebeest follow the grass, is plausible, though not yet certain. Picture the late Cretaceous plains of North America, the wide sky, the long, flat distances, and, moving across it, a herd of hadrosaurs, dozens of them, hundreds of them, their footsteps pressing the soil flat, their calls carrying across the open ground, moving together towards something only they understood, following an instinct laid down across thousands of generations. The urge to move, to follow the season, to travel toward abundance, is one of the oldest motivations that life has. It moved through the Cretaceous on heavy feet, and it moves through the modern world still. Some dinosaurs were nocturnal, or at least active at night, and their large eyes were built for seeing in the dark. The eyes of dinosaurs do not survive as fossils. Like all soft tissue, they decompose without leaving a direct record. But the orbit, the bony socket in the skull that held the eye, does survive. And from its size relative to the skull, scientists can make inferences about how large the eye was and how it was adapted. Some small theropods, particularly the troodontids, had very large orbits relative to their skulls. This is exactly the pattern seen in nocturnal animals today. Owls and tarsiers and bush babies, animals with enormous eyes for gathering as much light as possible in the dark. Beyond the orbit size, there is a structure called the sclerotic ring, a ring of small bones inside the eye that helped maintain its shape. In many dinosaurs, this ring is preserved, and the proportions of the sclerotic ring can tell us whether the eye was more like a daytime eye or a nighttime one. Velociraptor, based on its sclerotic rings, appears to have had eyes adapted for low light. It may have been crepuscular or nocturnal, hunting in the soft grey hours of dusk and dawn, or in the darkness between the stars of the Cretaceous night. A world that never fully slept. Predators moving through the ancient dark. Eyes wide open in the Cretaceous night, reading the shadows for movement, reading the air for scent, patient and precise and utterly alive. The night has always belonged to those willing to adapt to it. That truth is older than any of us. The intelligence of dinosaurs has long been underestimated, and recent research suggests that some were remarkably capable animals. For a long time, the dinosaur brain was dismissed as small and simple, adequate for basic survival but not for anything we would call cleverness. This view has changed substantially. Brain endocasts, the natural casts formed when rock fills the interior of a skull, preserve the outer shape of the brain. And CT scanning allows scientists to create three-dimensional models of what the brain looked like. From these models, the relative size and structure of different brain regions can be estimated. The large theropods, like Tyrannosaurus Rex, had olfactory bulbs, the parts of the brain dedicated to smell that were enormous relative to the rest of the brain. Tyrannosaurus likely had an extraordinary sense of smell, capable of detecting prey at great distances, reading the air with a chemical precision we can barely imagine. The small, fast theropods, particularly the troodontids, had relatively large brains overall, with expanded regions associated with complex behavior in modern birds. Troodon, in particular, had one of the largest brain-to-body size ratios of any non-avian dinosaur. Some researchers have speculated, somewhat playfully, about what might have happened had the dinosaurs not gone extinct. The troodontid lineage, given another few tens of millions of years, might have continued developing in the direction of increased brain complexity. It is a thought experiment with no real answer, but it opens a doorway onto something interesting. The path to intelligence is not uniquely human. Evolution has explored it before and will explore it again. We are one of many experiments the universe has run, and the dinosaurs were another, running for a great deal longer than we have. The sounds of the ancient world are partly recoverable through the insects and frogs preserved in amber. Amber is fossilized tree resin, and it has a remarkable capacity for preservation. Insects, spiders, feathers, plant material, even small vertebrates have been found trapped and preserved in Mesozoic amber, looking almost exactly as they did the day they were captured in the sticky resin. From the Cretaceous amber of Myanmar, of the Baltic, of Canada and New Jersey, an astonishing array of ancient life has emerged. Beetles, flies, ants, mosquitoes, flowers, spores, bird feathers, even a tiny snake, and several complete baby dinosaurs. But amber also preserves things less tangible. Researchers have extracted information from Cretaceous amber that tells us about ancient atmospheres, about the chemistry of long-vanished air, about what the world smelled like in the age of dinosaurs. And there is research suggesting that the insects preserved in amber can tell us about the soundscape of the ancient world. Some insects produce sounds by structures on their wings, and those structures, preserved in amber, can theoretically be analyzed to reconstruct the pitch and frequency of their calls. An ancient cricket, frozen in resin for 100 million years, still carries within it the memory of its own song. The specific frequency of the call it made on the evening it became trapped. Still there, encoded in the perfect amber light, waiting to be read. The ancient world made sound. It sang and clicked and hummed and roared. Even now, in the deep silence of the stone, the echo of that song persists, waiting for ears patient enough to find it. The discovery of soft tissue remnants in some dinosaur fossils has opened extraordinary new windows into the biology of ancient creatures. In 2005, a paleontologist named Mary Schweitzer published research describing the recovery of soft tissue structures from a Tyrannosaurus Rex bone. When the bone was demineralized in acid, what remained were flexible, translucent structures. Structures that looked like blood vessel channels and cells. The discovery was met with considerable skepticism. Soft tissue, organic material, was not supposed to survive 68 million years. The chemistry of preservation simply should not allow it. but subsequent research has confirmed the finding in multiple specimens and from multiple laboratories. Molecular traces, fragments of proteins, including collagen, have been recovered from several dinosaur fossils and analyzed. The collagen sequences recovered from Tyrannosaurus Rex show their closest resemblance to the collagen of modern birds and crocodilians, consistent with everything else paleontology knows about dinosaur relationships. This does not mean, as some popular accounts have suggested, that dinosaur DNA has been recovered. DNA is far more fragile than protein and degrades far more rapidly. The oldest reliably recovered DNA comes from specimens only a few 100,000 years old at most. Dinosaur DNA, if it ever existed in fossilized form, would have long since fragmented beyond any possibility of reading. But the fact that any original organic material survives at all, any fragment of the actual physical substance of a Tyrannosaurus, is extraordinary. It is a thread, however thin, connecting the present to the deep past. Not just a stone copy of life, but a genuine remnant, a fragment of the actual material from which that great and ancient creature was made. The line between past and present is thinner than it sometimes seems. Some of the most recent paleontological discoveries have come not from fieldwork, but from the re-examination of old collections. And there are still undescribed specimens sitting on museum shelves around the world. When paleontologists go into the field, they bring back more material than can be immediately studied. Some specimens are prepared and described within a few years. Others wait, sometimes for decades, wrapped in plaster jackets in museum storage rooms, waiting for the right researcher, the right question, the right technology to make their secrets visible. New imaging techniques, particularly CT scanning and synchrotron analysis, have made it possible to examine fossils in entirely new ways. Bones that were once considered featureless have revealed hidden structures when scanned. Skulls that could not be safely removed from their matrix have had their interiors digitally explored. Soft tissue impressions, barely visible to the naked eye, have been made clear under different kinds of light. This means that, in a very real sense, the great museums of the world, their storage rooms and drawers and long, quiet corridors, are as much a frontier of discovery as any badland or desert. Specimens collected a century ago are speaking again, using a new language of X-rays and computed tomography, telling their stories to researchers equipped to listen in new ways. The past is patient. It waits in drawers and basements and archive rooms. It waits through budget cuts and cataloging errors and the slow institutional amnesia that sometimes forgets what was brought back from the field. And then one day, someone opens a drawer, and a specimen that has waited decades to be seen gives up its secret. Quietly, without drama, the way all true revelations arrive. The first dinosaurs were small and fast, and they inherited a world still healing from catastrophe. The very beginning of the age of dinosaurs was not a triumphant arrival. It was a quiet and tentative emergence from the wreckage of another world. About 252 million years ago, at the end of the Permian period, the most severe mass extinction in Earth's history unfolded over thousands of years. Roughly 90% of all marine species and 70% of all land vertebrate species vanished. The cause was likely a combination of enormous volcanic eruptions in what is now Siberia, releasing greenhouse gases that warmed the oceans and acidified the seas, combined with cascading ecological failures that collapsed food chains from the bottom. The world that survived was impoverished. Simplified, many ecological niches emptied all at once. The great synapsids, the mammal-like reptiles that had dominated the Permian, were largely gone. Into this emptied world, a new group of archosaurs began to diversify, and among them, roughly 240 million years ago, the first dinosaurs appeared. They were small. Some of the earliest known dinosaurs, like Eoraptor from Argentina, were roughly a meter long, lightly built, quick, and bipedal. They were not the dominant animals in their world. Not yet. They shared their early Triassic landscape with other archosaurs, with large amphibians, with the ancestors of crocodilians. But they had something, some combination of anatomy and physiology and behavior, that gave them an edge as the world continued to change around them. And as the Triassic progressed, as other groups declined, the dinosaurs filled the space that opened. Quietly at first, then decisively. From a small and unassuming start, in a world still bearing the scars of catastrophe, they would go on to dominate the Earth for 165 million years. Beginnings are often like that. Quiet, unpromising. The first hint of something that will only later reveal its full scale. Dinosaurs likely used scent as much as sight and sound, and the ancient world was rich with chemical messages we can no longer read. Modern reptiles, birds, and mammals all use chemical signals to communicate. Scent marks on territory, chemical signals in saliva exchanged during social contact, volatile molecules released during moments of stress or arousal. This kind of chemical communication is ancient, far older than vision or hearing, and it almost certainly played a role in dinosaur life as well. The olfactory bulbs, the brain regions dedicated to processing smell, were large in many dinosaurs. Tyrannosaurus Rex, as mentioned, had extraordinarily developed olfactory processing. But, even in the plant eaters, the nasal anatomy suggests a meaningful investment in smell. Some researchers have proposed that the large skin glands, sometimes inferred from soft tissue fossils and skin impressions, may have produced scent secretions. Territory marking, individual recognition within a herd, mate assessment. The same fundamental conversations that animals have been having with chemistry since before the first backbone existed. The air of the Cretaceous carried messages we will never be able to read. The specific chemical language of animals, extinct for 66 million years. Information drifting on the warm air of ancient forests, understood instantly by every creature it reached, and completely lost to us. There is a kind of beauty in that. The world was communicating in ways that went entirely beyond what any fossil can preserve. The stone captures shape. It captures texture. In rare cases, it captures color. But the conversation carried on the air of the ancient world, the invisible language of chemistry and scent, that is gone completely. A silence that smells of deep time. The Spinosaurus may have been semi-aquatic, spending much of its life in rivers and shallow waters, making it unlike any other large predator we know of. Spinosaurus is one of the most enigmatic large dinosaurs ever found, and understanding it has been a long and complicated scientific journey. The original specimens were found in Egypt in the early 20th century and were described as a very large theropod with long spines on its vertebrae, forming a sail or hump along its back. Those specimens were destroyed during World War II, complicating research for decades. New material, discovered in Morocco over the past 30 years, has revealed a creature stranger and more fascinating than anyone expected. Spinosaurus had a long, narrow skull like a crocodile, with conical teeth suitable for catching fish. Its nostrils were set high on the skull rather than at the tip of the snout, consistent with an animal that spent time with its face partially submerged. Its front limbs were proportionally large. Its hind limbs were short and dense, and its feet were broad and paddle-like. A 2020 study proposed that Spinosaurus was not just a wader, fishing at the river's edge, but an active swimmer, moving through the water propelled by a tail adapted for undulation. If this interpretation is correct, Spinosaurus would have been the only large predatory dinosaur known to have genuinely lived in the water, hunting beneath the surface like a monstrous, feathered, sail-backed crocodile. This interpretation is still debated. Not all paleontologists are convinced. The anatomy is unusual enough that reasonable scientists can look at the same bones and reach different conclusions. But even the uncertainty is part of the story. Spinosaurus was strange. It was doing something that other large theropods were not. In a world of land-based predators, it had gone to the river, had made the water its home, had found its own solution to survival in a Cretaceous world full of competition. Strangeness is not a failure of fit. Sometimes it is the truest expression of what a living thing can become. The Cretaceous period ended not only with an impact, but with a world already under stress from enormous volcanic activity. The story of the end of the non-avian dinosaurs is more layered than a single catastrophic moment. While the asteroid impact was almost certainly the primary cause of the extinction, the world the dinosaurs were living in during the final millions of years of the Cretaceous was already experiencing significant change. In what is now India, a vast volcanic province called the Deccan Traps was erupting on and off for hundreds of thousands of years before the asteroid arrived. These eruptions released enormous volumes of lava and volcanic gases, including carbon dioxide and sulfur dioxide. The resulting changes to the atmosphere and climate were significant. Temperatures fluctuated. Sea levels changed. Some ecosystems were already under pressure. Whether these volcanic stresses were making the dinosaurs more vulnerable before the impact, or whether they were simply part of the background noise of a planet that was, as always, in motion, is debated. The evidence suggests that most dinosaur groups were still diverse and ecologically successful right up to the very end. The extinction was not a slow decline. It was sudden when it came. But the volcanic activity almost certainly made the aftermath of the impact worse. With the atmosphere already carrying elevated levels of volcanic gases, the additional input from the impact, the vaporized rock, the fires, the sulfuric acid rain, created a compounded catastrophe. The world was already complicated when the asteroid arrived. The ancient world was never simple. It was always layered, always multiple causes braided together, always a more complex story than the simplest telling allows. That too feels true to life. Very few endings are truly single events. They are the culmination of many things arriving at once. After the extinction, mammals rose to fill the world the dinosaurs left behind. But they were not starting from nothing. For much of the Mesozoic era, mammals existed as small, nocturnal, largely insectivorous creatures. They were present in dinosaur ecosystems from the Triassic onward, but they were not dominant. The large body sizes, the daytime ecological roles, the aerial and aquatic niches, all of these were occupied by dinosaurs and their relatives. Mammals had diversified quietly in the margins. There were small gliding mammals in the Jurassic. There were swimming mammals and burrowing mammals. The range of body plans was actually broader than was once assumed. But the ceiling was low. Large body size was not available to them, while the dinosaurs occupied those ecological spaces. When the extinction removed the large non-avian dinosaurs, that ceiling disappeared overnight. In geological terms, the mammals that survived the extinction found themselves in a world with vast ecological vacancies. Open forests and plains with no large grazers, river systems with no large aquatic predators, canopies with new opportunities for large, mobile climbers. Within 10 million years of the extinction, mammals had diversified to fill most of these niches. Enormous herbivores on the open plains, large predators in the forests, early ancestors of whales returning to the sea, bats filling the nighttime aerial niche that pterosaurs had vacated. It was one of the fastest and most dramatic ecological radiations in the history of life. Life does not mourn for long. It finds the open space, and it fills it. With every shape and size and strategy available to it, moving into absence with the unstoppable curiosity of a living world. And we are here, in part, because of that opening. We are what filled the space. We are the inheritors of the aftermath, the generation born into the vacancy left by the great and ancient ones. The social lives of dinosaurs were likely far richer than the bones alone can tell us, and behavior leaves almost no fossil record. Behavior is the ghost in the fossil record. Bones tell us shape and size. Isotopes tell us diet and movement. Growth rings tell us age. But how a dinosaur spent its day, the texture of its social interactions, whether it played, whether it comforted members of its group, whether it had preferences and moods and individual personalities, almost none of this leaves a physical trace. What we can do is look at the living groups most closely related to dinosaurs, the birds and the crocodilians, and think carefully about what behaviors they share. Birds are enormously social in many species. They form long-term pair bonds. They recognize individual members of their group. Many species engage in elaborate courtship displays. Some cooperate in raising young. Some mourn their dead. Some play, even in adulthood. Crocodilians, often thought of as solitary, actually show more complex social behavior than their cold-blooded reputation suggests. Nile crocodile females guard their nests fiercely. Some species appear to tolerate each other in ways consistent with social hierarchies. Young crocodilians make calls that prompt immediate responses from adults. Given these two reference points, the full and complex social world of birds on one side, and the more restrained but still present social behavior of crocodilians on the other, it seems very likely that at least some dinosaurs had rich social lives. Herding behavior is suggested by bone beds containing dozens of individuals of the same species. Nesting colonies suggest the tolerance of close proximity during vulnerable times. The elaborate display structures on many dinosaurs suggest a sophisticated visual language. A Parasaurolophus calling low and resonant across a Cretaceous dawn. A group of Triceratops recognizing each other by the pattern of their frills. A mother oviraptor pressing her arms more tightly around her eggs as something large moved nearby in the darkness. These are not fantasies. They are inferences grounded in biology, pulled carefully from the available evidence. The social world of the dinosaurs was real. It was just silent in the ways that matter most to stone. Paleontology has been shaped by remarkable women whose contributions were not always recognized in their time. The history of science has often failed to record the contributions of women fairly, and paleontology is no exception. But women have been central to the field since its earliest days. Mary Anning was a working-class fossil hunter in early 19th century England, operating from the Jurassic coastal cliffs of Dorset. She found the first complete ichthyosaur skeleton to be scientifically recognized. She found the first complete plesiosaur. She found a pterodactylus. Her discoveries were fundamental to the development of paleontology as a discipline. But because she was a woman, and because she was poor, she was largely excluded from the scientific societies of her time, and her name was often omitted from the papers describing her finds. More recently, Mary Schweitzer's work on soft tissue preservation in dinosaur fossils, mentioned earlier, has been among the most significant and controversial contributions to the field in decades. Her persistence in pursuing and defending findings that the scientific community initially rejected has changed what we understand about the limits of fossil preservation. Lowell Dingus and Catherine Forster and Christy Curry Rogers are among the many researchers whose work has quietly expanded the field. Their names are less famous than the creatures they describe, but their care and patience and intellect are in every new species added to the tree of life. The story of paleontology is not just the story of the animals in the rock. It is also the story of the people who found them, who bent down in a hot desert or a cold cliff face, and saw something in the stone that no living person had ever seen before, and then devoted years of their lives to understanding it. Fossilized dinosaur dung, called coprolites, tells us what dinosaurs actually ate, sometimes with extraordinary specificity. The study of coprolites, fossilized feces, is one of the more quietly fascinating corners of paleontology. It is also one of the most direct windows into diet that the fossil record offers. A coprolite from a Tyrannosaurus Rex found in Saskatchewan contained crushed fragments of the bone of a young ceratopsian dinosaur. The fragments were from the humerus, an arm bone, and they had clearly been consumed and partially digested. This was direct evidence, not inference, that Tyrannosaurus crushed and swallowed bone. Coprolites from plant-eating dinosaurs have been found containing conifer wood fragments, suggesting that some sauropods consumed woody material as well as leaves. Others contain spores and pollen, telling us which specific plant families formed part of the diet. Even the bacteria preserved inside coprolites can be analyzed. The microbial communities in the ancient gut, the ecology of digestion in a world long vanished. Each coprolite is a small and peculiar archive, mundane in origin, extraordinary in what it preserves. There is something gently humbling about this kind of science. The grandeur of the ancient world, the 65-million-year saga of the dinosaurs, is illuminated not only by magnificent bones and towering skeletons, but by fossilized evidence of the most ordinary biological processes. Every part of a life leaves a record if the conditions are right, even the parts we would rather not think about. The climate of the Mesozoic era was warmer than today's, with no permanent ice caps and seas lapping across large parts of the continents. The world in which the dinosaurs lived was warmer than ours, significantly warmer in most periods. Atmospheric carbon dioxide levels were higher than they are today, and the greenhouse effect kept average global temperatures elevated. There were no permanent ice caps. The poles were cold and seasonal but not glaciated. Sea levels were substantially higher than today, because there was no large volume of water locked into ice sheets. Shallow interior seaways divided continents that today are continuous. North America, for example, was split down the middle by the Western Interior Seaway, a warm, shallow sea that stretched from the Arctic to the Gulf of Mexico during the late Cretaceous. This sea was full of life. Mosasaurs and plesiosaurs hunted through it. Large fish and diving birds pursued smaller prey beneath its warm surface. Its shores were home to the hadrosaurs and ceratopsians that we associate most closely with the last chapter of the dinosaur age. The warm climate also meant that vegetation grew abundantly across a broader range of latitudes. Forests reached much farther toward the poles than they do today. The world was green in places that are now tundra or ice. It was a gentler version of the planet, in some ways. Warmer and wetter and more uniformly hospitable. The kind of world in which large, warm-blooded animals with high energy requirements could find food reliably across most of the globe. A world shaped differently, inhabited differently, breathing differently. And yet, beneath the different geography and the different climate, the same fundamental processes. Sunlight falling on green leaves, water moving downhill to the sea, life finding every opening available to it. The same planet, wearing a different face. Dinosaurs inspired the first scientific understanding that species could go extinct, and their fossils changed how humanity saw the history of life. Before the 19th century, the dominant view in Western thought was that species were fixed, created once, unchanging, and still present or simply undiscovered if they seemed to be missing. The idea that an entire group of creatures could have existed dominated the Earth for millions of years and then completely vanished was genuinely difficult to accept. The great fossil bones being unearthed in England and Europe in the early 19th century forced a rethinking. These were clearly not the bones of any living creature. They were too large, too strangely shaped, too different in their proportions from anything alive. Cuvier, the French naturalist who did so much to establish paleontology as a discipline, was among the first to argue convincingly that extinction was real. That species could be lost, that the history of life on Earth was not a stable and static thing, but a process of change, of loss, of replacement. The dinosaurs were central to that realization. Their bones were the evidence that the living world had not always been what it is today. that Earth had once been inhabited by creatures utterly unlike anything still alive. That deep time was real and vast and full of surprises. They did not just change our understanding of the past. They changed our understanding of what the present is, not the final, permanent state of things. Just one more moment in an ongoing and endlessly changing story. A story that began billions of years before us and will continue, in whatever form, long after we are gone. Some dinosaurs slept with their heads tucked under their arms, exactly as birds sleep today. This is one of the most quietly beautiful details that paleontology has given us. A Mei Long, whose name means soundly sleeping dragon, was a small troodontid found in China, preserved in the exact posture of sleep. Its legs were folded beneath its body. Its neck was curved back over its shoulder. Its snout was tucked beneath the wing-like arm, in a posture identical to the sleeping posture of modern birds. It had been asleep when it died. Preserved, perhaps by a sudden burial in volcanic ash or a rapid sediment flow, in the exact position in which it was resting. For 125 million years, it lay in that posture in the dark. And when it was found, it looked like a bird that had simply not woken up yet. There is no way to see that specimen and not feel something. Not just the scientific significance, though it is considerable, but the simple and overwhelming intimacy of it. A small creature, asleep, head tucked in, body warm, in life. All the world going on around it while it rested in the quiet dark. The way you are resting now. The posture of sleep is ancient. The need for it is ancient. The surrender to rest, the tucking inward, the letting go of the world for a few hours. This is something you share with a small feathered creature that lived 125 million years ago. You are not separate from the ancient world. You are part of the same long story, resting in the same dark, tucked quietly into the same turning world. The study of dinosaur posture and movement has revealed that many species were far more graceful than early reconstructions suggested. For much of the 20th century, museum skeletons showed dinosaurs in upright, almost human postures. Theropods standing bolt upright like kangaroos, tails dragging behind them on the ground. Sauropods rearing up on hind legs, front feet raised. These postures were partly borrowed from the mammal and reptile models available at the time, and partly the result of mounting bones in whatever positions allowed them to be displayed impressively. Biomechanical research over the past few decades has corrected these postures substantially. Theropods carried their bodies roughly horizontal, balanced over their hips, with the tail held out behind them as a counterweight. Their movement was not an upright shuffle, but a fluid, forward-leaning stride, more like a large running bird than anything else. The tail, rather than being dragged, was a dynamic structure. In many theropods, it was stiffened by bony tendons that ran along the vertebrae, holding it rigid and level. It moved with the body, swinging slightly as the animal ran, acting as a stabilizer and counterbalance for every shift of weight. Sauropods, rather than rearing, almost certainly held their necks in a gentle upward curve when at rest, like a massive, slow-moving swan. The angle of the neck varied by species, and some could probably raise or lower it considerably, but the image of a sauropod crashing upright on its hind legs is almost certainly wrong. These corrected postures make the animals feel different, more balletic in their own enormous way, more fluid, more like the living things they were, moving through a world that asked them to be precise and efficient, not theatrical. A Tyrannosaurus running toward you, body horizontal, tail out straight, those small arms held in close, the enormous head low and steady, covering ground with each stride at a terrifying pace. That is the real picture. Not a monster from an old movie, but something far more precise, far more alive. Some of the largest known dinosaurs come from South America, and Argentina in particular has yielded giants that surpass anything found elsewhere. The Patagonian region of Argentina has been one of the most productive places for dinosaur discovery in the world over the past 3 decades. The conditions there, dry badlands, exposing Cretaceous and Jurassic rock layers at the surface, combined with active research programs and local communities engaged in fossil discovery, have produced a remarkable series of finds. Argentinosaurus, described in the early 1990s, was for a time considered the largest land animal ever to have lived. Estimates of its weight vary enormously, from 60 to 100 tons or more, because only partial remains have been found. But even the most conservative estimates put it among the largest animals ever to walk the earth. Then came Patagonian maiorum, described formally in 2017 and represented by multiple individuals, allowing more reliable size estimates. Patagonian was enormous, roughly 37 meters long and estimated at 60 to 70 tons. A femur, the thigh bone, that stands taller than most people. Vertebrae the size of small cars. To understand how such an animal could exist at all is a fascinating exercise in physiology and engineering. The respiratory system must have been extraordinarily efficient. The bones, though enormous, were hollow and lightweight, more like the bones of birds than those of elephants. The cardiovascular system, pumping blood through a body of tens of tons, must have been a remarkable piece of biological engineering. And yet, it worked. For millions of years, animals this size walked across the Cretaceous floodplains of what would become Patagonia. The ground they walked on is still there, buried under newer rock, occasionally exposed by the slow work of water and wind, still carrying the impression of their impossible weight. The largest creatures that ever lived on land are not in our world. They are in the stone beneath South American skies, still vast, still present in their own quiet way, still remarkable after all this time. The great bone beds of Western North America are sites where hundreds of dinosaurs were buried together, and they tell stories of catastrophe and community. Across Alberta and Montana and the Dakotas, there are places where the rock gives up its dinosaurs in extraordinary numbers. Single sites containing the remains of dozens, sometimes hundreds, of the same species, mixed together in a layer of bone that speaks of a single catastrophic event. A massive Centrosaurus bone bed in Alberta contains the remains of perhaps thousands of these ceratopsian dinosaurs. The most likely explanation is a river crossing gone wrong. A large herd moving together, attempting to cross a flooding river. Many drowning in the current. their bodies carried downstream, deposited together at a bend in the ancient waterway. A mass grave written in stone. These bone beds confirm what the anatomy and the nesting sites only suggested. These animals moved in groups, large groups large enough that the loss of dozens or hundreds at a single crossing was not the loss of the whole. The herd continued. The survivors crossed elsewhere. Life carried on in the way that life always does. Around the losses, through the gaps, finding the path that remains open. There is also something deeply poignant about these sites. So many animals, moving together with a shared purpose, trying to get somewhere. And the record of their attempt, preserved in the rock for 75 million years, still visible to anyone patient enough to find it and careful enough to read it. The ancient world was full of ordinary moments made extraordinary only by time. A herd crossing a river. Just another day in the Cretaceous. Except that the stone remembered. And we are still listening. Each season in the ancient world had its own texture, its own rhythm, and the dinosaurs lived inside those rhythms, the way all living things do. We tend to think of the deep past as static, a fixed image suspended in amber. But the Mesozoic world was seasonal. It breathed in and out with the year. Wet seasons and dry seasons, warm months and cooler ones, the rising and falling of rivers, the greening and browning of the vegetation, all of it cycling as it always has, with the tilt and orbit of the Earth. Dinosaurs lived inside those cycles. Feeding patterns changed with the seasons. Breeding was likely seasonal in many species. Time to coincide with the best conditions for egg incubation and hatchling survival. Migrations, where they occurred, were driven by the seasonal availability of food and water. There were mornings in the Cretaceous, when the light came in at a low angle through ancient trees, and the air was cool and damp with recent rain. There were dry afternoons when dust moved across open ground in slow columns. There were evenings when the sky above an ancient floodplain turned the same colors it turns today, orange and rose and deep violet, and the insects rose in clouds above the waterline, and something large moved slowly through the trees toward the river. These moments happened. Millions of them. Billions of them. Each one fully real, fully present to the creatures who experienced it, as real and immediate as the moment you are in right now. The universe has always been present in its moments. This one is no different from the ones that came before. The evening light falling on living things, and the world turning gently toward night. And so, dear listener, our long and gentle walk through the age of dinosaurs draws softly to a close. We have traveled a great distance tonight, though you have not moved at all. We walked back through layer after layer of stone and time, through ancient forests that no longer stand, through shallow seas that no longer exist, through a sky crossed by wings whose owners have been gone for 66 million years. We watched enormous creatures move slowly through Jurassic shadow. We found nests tended by careful mothers. We read the healing bones of survivors. We felt the weight of footprints pressed into ancient mud. We glimpsed color and feather and the warm inner fire of creatures that were so much more alive than we ever gave them credit for. We sat beside a Stegosaurus as its plates caught the morning light. We heard, or almost heard, the low resonant call of a Parasaurolophus carrying across a Cretaceous plain. We stood beneath the neck of a sauropod and looked up at a canopy it alone could reach. We watched a small feathered dinosaur settle onto its nest and spread its wings around its eggs in the still air of an ancient evening. These creatures were not shadows. They were not dim and distant outlines in the rock. They were vivid. They were warm and particular and fully present in their world. They had lives with texture, with the specific weight of each moment, with hunger and recovery, and the quality of late afternoon light across an ancient land. And though they are gone in one sense, they are not gone in every sense. Their descendants fill the sky above you. Their shapes persist in the stone beneath you. Their chemistry lingers in the collagen of ancient bone. Their story is written in the very structure of the birds that will sing outside your window when the morning comes. The world is deeper than it appears. Beneath every ordinary thing, there is a history so long and so full of life that it humbles the mind into quiet, into wonder, into stillness, into something very close to sleep. Let your body settle now into the surface beneath you. Feel the weight of it, the way it holds you, the way you do not have to do anything at all to be fully supported. Let your breathing slow to the pace of something ancient, something patient, the breathing of a world that has been here for 4.5 billion years and has learned to take its time. Picture, if you like, a quiet Cretaceous evening. The air warm and thick with moisture. The light coming in low and golden through the canopy. A river somewhere nearby, moving over smooth stones. And somewhere in the middle distance, large shapes moving slowly through the trees. Unhurried, following whatever they follow, toward a place they know. Let the image soften. Let the colors blur gently together. Let the sound of the river become a kind of breathing. Let the shapes dissolve into warmth and shade. The ancient world is not asking anything of you. It has been here far longer than your worries. It will be here long after the last thought fades. If your eyes are still open, you can gently let them close. There is nothing left to watch, nothing left to solve tonight. The world outside will continue to turn at its own pace, the way it always has. The stars are still above you, even though you cannot see them. The stone beneath you holds its millions of years of quiet patience. And the birds in the trees outside your window are, in the deepest and most literal sense, the last children of an ancient and remarkable dynasty. Still here, still warm, still singing. Let everything else drift. Let the day go. Let the ancient world hold you gently in its enormous, patient, 66 million year old quiet. Close your eyes. Breathe slowly. And drift, softly and without effort, into rest. Into stillness. Into sleep. Into the deep and dreamful dark, where the ancient world waits quietly and there is nothing but peace. Good night.